আচ্ছা সুদীপ, আমি সেশনটা রেকর্ড করছি,
Sure,
ঠিক আছে?
sure.
ওকে, সো we have a special lecture today on option pricing with levy processes. So the speaker is Sudeep Chandra. He is working for Genpact Digital at Boston currently, but he is an alumnus of ISI Kolkata, and he has recently submitted his PhD thesis on this topic. So he would be giving you a little bit of introduction on levy process and also give you a glimpse of what he has done in the thesis. So Sudeep, this is an MStat second year class. So basically these are all from statistics background, but they have already been taught the basics of Ito process and the corresponding Black-Scholes pricing. So hopefully they remember that because it just finished. So now you can start. Over to you. Thank you.
Okay, thank you so much, Professor Diganta Mukherjee, for the introduction. So let me give you about myself. Okay, I'm actually Sudeep Chandra, working in Genpact Digital in Boston as the assistant vice president, and mainly working for the company in the different quantitative solution for the different line of businesses. Okay, so my research was in this particular topic, the option pricing with levy process. Okay, and today's discussion will be on that particular topic. So I'll be covering a couple of things, a couple of items. First, like what is options in the financial market. Probably all of you know this. And second is like some of the empirical facts about the stock price. Third, we'll be discussing about levy process, the basic definitions. Fourth, how we can use or how we can leverage the leverage the levy process for pricing stock or modeling stock price. Fifth, we'll be discussing about arbitrage-free pricing concept, and finally, we'll be discussing about the hedging strategies. I think you have gone through hedging methods are also in the previous lectures presented by Professor Diganta Mukherjee. So let's start. Okay, so what are the options? So options are basically different type of contracts traded in the financial market, especially traded in the different exchanges. Okay, so now question is why the contracts are required. So contracts are required, or these options are required typically to offset the loss due to the change in price. It may so happen that you are holding a stock and the price will say maybe at certain level, now it may decrease, right? So whenever it is decreasing, then you will incur a loss. So who will compensate that loss? So there is a contract like options that you can actually use it to offset the loss. So contract price will be increasing if the price of the underlying asset will be decreasing. It's something like that. Now, there are made various type of options in different domains of the financial sector. Now, a couple of type of options that I worked, they are called exotic options. So one of them is called the Asian option. Asian options are options where the payoff is typically depends on the average of the stock price. Okay, so we'll be discussing in detail that how payoff looks like in the next couple of slides. Okay, the second one is the barrier option. This option has a typical behavior, like there are different barriers of the stock price. So if it overshoots the barrier, okay, then you will get zero payoff. Okay, and otherwise you'll get a normal, payoff. That normal payoff, like any vanilla call option like that. So that's a kind of nature. The third one is that loop back option. Loop back option is an option where the payoff typically depends on the lowest or the highest price of the stock. So it is a kind of maximum or minimum of the stock price. It actually depends on that. Okay, now let us take that, let us go a little deep into that Asian option dynamic, Asian option payoff dynamics. Here you see I have taken a stock price ST, and if this is like in a sum of stock price, okay, over time, I'm integrating this. And for fixed strike, option, we have actually payoff dynamics like this. And this is the strike price. Okay, so I'm taking basically averaging. Okay. And for floating style, I'm taking this, the stock price minus average. Okay, and this is for call, and it can be for put as well. Okay. And if I have a marginal measure, okay, you can call it like a distribution measure Q in the market. Okay, so then the pricing formula is like this, where this is the payoff function. So what you notice that what I'm doing actually, I'm taking expectation under a measure Q, okay, and then I'm doing the discounting. So that's a kind of discounted price at the present, okay, and I know the future payoff like this. So let us let us go through the dynamics of payoff dynamics of barrier option. So barrier, you see, I have taken a barrier B, okay, and similar to that, fixed and floating strikes are there. So what I'm doing the payoff here is that the function is that S minus K, S is the stock price and K is the strike price, and I have taken the indicator is less than or equal to B. So the value is is non-zero when S less than B. And if it is like up and out, it can be in other way, like it can be down and out also. So in that case, if it is greater than B, then I will get some payoff, otherwise it's zero. So the question is that how to actually compute this in all cases. Like this is one typical dynamics of the Asian type. Second one is for the barrier. Okay, so you can understand like the challenges is computing the expectation. Now third one is the loopback option. So what I have taken is that MT is a maximum of the stock price. Okay, and the payoff is basically maximum minus the stock price. Okay, and as usual, what I'm doing actually doing the discounting and taking the expectation. So in all cases, see, I don't know the first case in the Asian option, I don't know the distribution of the average. Okay, even I don't know the distribution of the stock. The stock maybe if it's a Black-Scholes, I know the distribution, but even in case of Black-Scholes, it is pretty difficult to find out the distribution of the average. And similarly for here, that overshoot process, okay, or the distribution of this particular payoff is not known. And for loopback option, of course, even if I know the distribution of the stock price, it is very hard to find out the distribution of the maximum of the stock price. So in all cases, finding the distribution of the payoff is not so straightforward. Okay. Now, what we'll be studying, we'll be first studying the empirical, okay, some of the facts of the stock price. See, what I have done is that I have plotted here some stock price for taken the value of the stock price taken from Google, some of them from Lilly and Microsoft, and I have plotted here. You see, looks like the distribution is not really normal. Okay, so we'll study that one. So what I did is that I plotted a QQ chart, QQ plot. Okay, and you see here the tail is fat. Okay, so it is no way a normal distribution. Okay, and I did a couple of tests like JB and KS, which is also showing that it is not normal. Okay, so these are the observations from the stock price facts. Okay, that it is asymmetric. You see here, this is asymmetric, skewness is there, and fat tail presence in all case, and non-normality is not accepted. Okay, and QQ plot also saying that there is some fat tails. So what process would be best for modeling this kind of scenarios? Okay, So what we are doing is that we are proposing a process called a Levy process. We'll be discussing about the features in a couple of more slides later on. But what I did is I've taken a sample of Levy process called NIGE process. Okay, and you see, I try to plot with a normal distribution and see it is not fitting well. Okay, but if I take the Levy, one of the instances of the Levy process called NIG process, okay, and then this is fitting pretty much well. Okay, so probably the Levy process in this particular scenario, when these kind of phenomena are there, probably Levy process would be good fit. Now in the Levy process, why it is good fit? Because in the stock price dynamics, as you observe here, that there are sudden spikes actually. So here you see spike, here there is a sudden jump, and sudden fall is also here. Okay, so these kind of sudden jumps are there. That's why this is not following any normal distribution. This is following some other distribution, some other heavy tail distribution, like say Levy. Okay, so up to this, any question? Hello.
Are there any clarifications, students?
No, sir. No, sir.
Okay, fine, perfect. Okay, so let us go to the definition of the Levy process now. Okay, so Levy, first we define couple of basic definition. Okay, that will be required to define the Levy process. Okay, so first we'll define the random measure. What is random measure? Let us take MT is a Poisson process of counting number of jumps at the different times, say T1, T2, and Tn. Okay, so this is like a counting process. Okay, and I'm defining this way. MT is a number of jumps between say 0 and T. So mathematically I'm defining this way. Okay, number of jumps, and where Ti is belongs to 0 to T in this case. Now what I'm doing actually for this counting process, I'm defining a random measure. Okay, so random measure for this counting process. Okay, and I'm defining this way. In is a random measure, which is the number of jumps, okay, that belongs to A. A is a measurable set of positive, because what this time is a positive. Okay, so that's why actually I'm taking this measurable set as a positive set. Okay, so this is the measure I'm defining. Now if I'm defining the measure this one, now one thing is that I should tell, which is like omega. Omega is a scenario for particular path. Okay, so it can go different paths for the different randomness. Okay, so scenario is so omega is a scenario of a particular path. So random measure for a particular scenario, okay, given a measurable set, is defined by this. Now, if this is the measure, then I can probably compute the expectation of the measure. Okay, so expectation is the average is lambda into mod of this. Okay, so mod of the into the size of the set. Okay, and the size of the set is basically the integral. Okay, I can define this way. It is a Lebesgue measure of A. So, now I have defined the random measure. Now let's come back to Poisson process defined in terms of random measure. So in that case, the final random measure, final Poisson process, I can define as an integral of integral between 0 to T, and I will take this particular measure. So what it signifies is the summation of number of jumps. Okay, next what I'm doing, I'm defining now a compensated Poisson process. So compensated Poisson process is nothing but just, I'm subtracting the mean, okay, from the process. So here, you see, I'm defining as a n tilde and subtracting the mean to make it a mean zero mean process. And obviously there is a very simple part is this. And since this, you can notice that since this is like a Poisson process, and we can write like this lambda into this. Lambda is already defined in the process, the intensity of the jump. Okay, now what we'll be doing, we'll be defining the Cadillac, a process called Cadillac process, or Cadillac function rather. Okay, now Cadillac function is a right continuous with left limit function. Okay, it's function which is right continuous with left limits, and I can define like this. Now, for the left part, which is, left part is basically discontinuous in this particular Cadillac function. And discontinuity is defined by this. So I can define like, discontinuity is ft and ft minus. And the right part is basically continuous, so ft is equal to ft plus. So the left hand side, there is a discontinuity, but the right hand side is smooth. It is continuous. So it is a function like that. Now what I will do, I will define a jump measure of this kind of process, Cadillac process. So jump measure is basically a random measure associated with this Cadillac process. Okay. If it is a Cadillac process like xt, then obviously jump we can define like st t minus, okay, and corresponding measure nta is equal to basically the number of jumps occurring between 0 to t, and whose magnitude of the jump, which is like delta s, belongs to some set. Okay, so this way I can define the jump measure. Now I am actually defining the Levy process. Now the Levy process is nothing but a Cadillac process. So Cadillac process we defined here. Okay, and Levy process is a Cadillac process, but has certain properties. What are the properties? Properties, it has independent increment. You see the differences are basically, these are the differences, these are independent. Also, it has a stationary increment. Stationary increment means this xt t plus h minus t is independent of t. Okay, and third one is that it has stochastic continuity. Stochastic continuity is, I'll take xt plus h minus t and its absolute value, and the probability of this greater than 0 is almost 0. Okay, so this way I'm defining a process which is a Levy process. Now there is another interesting property of the Levy process, which is called infinite divisibility. So let us consider a Levy process defined by say x, and x if I can split like this, okay, with different independent variables like x1 to xn. Now if the Levy process x has a distribution psi x, then it can be written like the psi x for the entire Levy process is basically the power of power of individual characteristic function of the variables. So these are the splitted variables. So this is having actually having a characteristic function like this. So it will be the power of this. Now let's define Levy measure. Okay, so Levy measure I'm defining as the expected number of jumps of the Levy process xt per unit time and the size which is belonging to a set A. So I'm defining like expected number of jumps between some unit time and size of the jump belongs to A. So that's called the Levy measure. Now in the Levy process, we discuss about the definition, we discuss about the Levy measures. Now there is an interesting property of the Levy process that the Levy process can be written in three different parts. Okay, one part I am calling is that the continuous part. You are already aware of this for the Black-Scholes, model, that this is like a stochastic. This is the growth part. This is the stochastic part, and this is continuous. But there are discontinuous parts because of this jump. So these are two different parts. So Levy process, I can define with a Levy triplet. So Levy triplet is like with the growth, there is a growth, there is a continuous part on the stochastic part. For that, sigma square is there, or sigma is there. And for the jump, we have actually the Levy measure, which is new. And I have defined the Levy measure with this. Okay, so X, the Levy process can be defined with a growth, a stochastic part, and also a jump part, which is a discontinuous. And the Levy process actually follows certain square of nu x dx is, and also nu x, these are finite. So here you see that for mod x less than equal to 1, which is basically for the small jumps, and this is for mod x greater than equal to 1, this is for the large jumps. Okay, so these has to be finite. So how we can define Levy process? With the triplet, and we can define like this. Okay, now Levy process, if I define the Levy process with the Levy triplet, there is another interesting representation, which is called Levy engine representation, where the characteristics of the Levy process can be represented like this. So we can actually derive this from the earlier definition of the Levy process. We can derive, and characteristic function is like this. Okay, so now that was about the theoretical part. Now let us take some of the let us have a look at some of the examples of the Levy process. So one of the Levy process, they call it normal inverse Gaussian process. Where you see, I have taken three parameters, alpha, beta, and delta, and characteristic function is defined by this. And and there should be a Levy measure also, because the jumps are involved. So Levy measure for this NIG process is defined with this kind of function. And so if I want to define completely as a Levy process, okay, then obviously I have to define with the Levy triplet. And with the Levy triplet, you see the gamma is a growth, and there is no stochastic part. Here it's a pure jump type Levy process, okay, and there is a jump also, and the growth is defined by this. So here it is a pure jump type, and no and no stochastic part. So there is another another instance of Levy process we have, which is called the CGMY process, where the characteristic function is defined by this. Okay. And Levy measure, the expression for the Levy measure is like this. Okay, and this is also a pure jump process, where you see the growth is defined by this. So this is also another type of the Levy process. So now let us see one, how really the Levy process looks like. So if you plot this or try to simulate the Levy process, you will see the dynamics. It's like this. Okay, so you have noticed that there are various jumps actually occurring here. So this is one jump, this is another negative jump, this is also negative jump. So a lot of positive and negative jumps are happening. And if you plot this quantile plot, you will find this is not a normally distributed. It is showing all this heavy tail distributions. Okay, now, okay, up to this, any question? Any question up to this?
Yes, sir.
No question? Okay, fine. Okay, let's move on then. So now let us try to use the Levy process for stock price modeling. Okay, so what we are doing here is that we are considering this the initial stock price into e to the power zt, where zt is a Levy process. Okay, so I'm taking exponential of the Levy process. Why? Because the stock price cannot be negative, but if this Levy process can be negative and positive as well. Okay, so I'm taking the exponential of the Levy process. So that what we'll be doing is that we'll be going to the theory of pricing with that Levy process. Okay, first let us discuss about some of the pricing concepts. Okay, so before that, I'd like to know, is it understandable, or do you have any question before that, before proceeding the next section? No question? Okay, fine. Okay.
Sudeep, there is a problem. I made some mistake. This is a finite meeting. So can we rejoin? So students, I'll end this one and restart because it seems to be I made a mistake in logging in.
Okay.
So we'll just end this one and then restart, and please rejoin with the same link.
Sure. Sure. Sure.